Assalamu alaikum. This presentation will focus on two important sequential logic elements, the clocked RS flip-flop and the JK flip-flop. We will explore their structure, functionality, truth tables, timing diagrams, and typical applications. Before continuing, let me introduce myself. My name is Shifa Binte Faisal, bearing ID 123080028. This presentation explores the functionality and applications of clocked RS and JK flip-flops in digital logic and circuit design. We will discuss in brief. Now the question arrives, what is flip-flops? A flip-flop circuit can maintain a binary state indefinitely as long as power is delivered to the circuit until directed by an input signal to switch states. The major differences among various types of flip-flops are in the number of inputs they possess and in the manner in which the inputs affect the binary state. Flip-flops are basic memory elements in sequential logic. They store one bit of data and change state based on clock input and control signals. Unlike combinational circuits, sequential circuits use memory. Flip-flops are the building blocks that remember one bit of information. Their outputs depend not just on the current inputs but also on the past sequence of inputs controlled by a clock. The RS flip-flop is used to store binary information, for example 0 or 1. It consists of two inputs, set and reset. In RS flip-flop, R stands for reset and S stands for set. The flip-flop keeps its present state even when one or both inputs are deactivated. The flip-flop enters the 0 state when the reset input is activated and the 1 state when the set input is activated. A clocked RS flip-flop adds a clock input to the basic RS latch which contains R reset and S set input. It ensures that the state changes only occur on the active clock signal, making it synchronous with other circuit components. The behavior changes in RS flip-flop circuit only when clock equal to 1. It is generally implemented using NAND or NOR gates. Here is the graphical symbol of clocked RS flip-flop. We can see that the input R, C and S is here and the output Q and Q bar is here. Here is the logic diagram of clocked RS flip-flop. RS flip-flop can be constructed using basic logic gates such as NAND gates or NOR gates. This is shown a RS flip-flop constructed using NOR gate. Same we can construct a RS flip-flop using a NAND gate. Working of RS flip-flop depends on its inputs. In initial state, output can in any state set or reset. In set, S equal to 1 and R equal to 0. Conversely, in reset, S equal to 0 and R equal to 1. When R equal to 0 and S equal to 0, it holds the current state. When R equal to 1 and S equal to 1, it falls under undefined forbidden state. This is the truth table of clocked RS flip-flop. Here S is the set input, R is the reset input, Qn plus 1 is the next state and state tells in which state it enters. Here we can see that when CLK or clock equal to 0, the flip-flop holds its state. When clock equal to 1, we get normal RS behavior. The 1-1 condition is invalid and should be avoided because it creates an undefined output. The characteristic equation tells us about what will be the next state of flip-flop in terms of present state. The equation is Qn plus 1 equal to S plus Qn and R bar. Here S is the set input, R is the reset input, Qn is the current state input and Qn plus 1 is the next state outputs. Excitation table basically tells about the excitation which is required by the flip-flop to go from current state to next state. Here Qn is the current state, Qn plus 1 is the next state outputs and S are the set and reset inputs respectively. The JK flip-flop is the form of sequential circuits which are applied as the basic elements of the digital memory. This JK flip-flop has two input lines J and K, clock line CLK, clear line CLR as well as preset line PR. Q and Q bar are its two output which are usually in the opposite state while operating. The JK flip-flop can also be called a bistable multi-vibrator since it has two stable steady states. The JK flip-flop is one of the most commonly used flip-flops because it removes the undefined behavior found in RS flip-flops. It has predictable behavior even when both inputs are active. This is the graphic symbol of clock JK flip-flop. We can see that the inputs are J, K and clock CLK and the outputs are Q and Q bar. This is the logic diagram of JK flip-flop. The JK flip-flop encodes feedback from the output to the inputs, enabling toggle operation. This feedback is the key difference from the RS flip-flop. The circuit diagram of JK flip-flop shows that two 3-input NAND gates are used in place of the original two input AND gates. The outputs at Q and Q bar are coupled to each gate's third input. Since the two inputs are now interlocked, the SR flip-flop's cross-coupling enables the previously invalid condition of S equal to 1, R equal to 1 to be employed to perform the toggle action. In a circuit set, the bottom NAND gate interrupts the J input coming from the 0 position of Q. In the reset state, the top NAND gate interrupts the K input coming from the 0 positions of Q. We can use Q and Q bar to control the input because they are always different. The flip-flop is toggled according to the truth table when both inputs J and K are set to 1. This is the truth table of JK flip-flop. Here we can see that when clock equal to 1, J equal to 0 and K equal to 0, the next state is no change. When J equal to 0 and K equal to 1, the next state is reset. When J equal to 1 and K equal to 0, the next state is set. When J equal to 1 and K equal to 1 also, the next state is toggles the current output. For example, Q becomes Q bar. On the other hand, when clock equal to 0 and J equal to don't care X and K equal to don't care X, the next state is no change. A JK flip-flop is a kind of sequential logic circuit that keeps track of binary data. Its characteristic table shows how the output Qn plus 1 changes using input J and K along with the last state Qn. Let's break down the characteristic table. There are 4 states to understand. When J equal to 0 and K equal to 0, no change state. Here the output Qn plus 1 stays the same. This means the next state Qn plus 1 is just like the current one Qn. When J equal to 0, K equal to 1, reset state. In this case, the next state is reset to 0, Qn plus 1 equal to 0. No matter what, the current state is Qn. When J equal to 1 and K equal to 0, set state, the next state gets set to 1 again, no matter what's happening in the current state Qn. When J equal to 1 and K equal to 1, toggle state. In this state, the output Qn plus 1 toggles. So if the current state is set, it will change to 0. If it's reset, then it flips to 1. The excitation table shows us which input combinations we should use for a JK flip-flop to get the output we want. Here X is don't care, Q is current state, Qn plus 1 is next state, and J and K are two input values. This table guides us on what input values to use so we can move from the current Qn to the next state Qn plus 1. Now let's compare the timing behavior of RS and JK flip-flops using waveform diagrams. Let's start with the JK flip-flop shown on the right side of the screen. As we can see, it includes a clock input and output changes happen only on the falling edge of the clock pulse, marked by red arrows at time points T1 through T8. This type of flip-flop is edge-triggered and synchronous, meaning it reacts only when the clock tells it to. For example, at T2, J and K are both 1. This leads to a toggle action so that the output Q changes from 1 to 0. At T4, J is 1 and K is 0, which is a set condition making Q go high again. Notice that the JK flip-flop waits for the clock's edge, making it more stable and predictable in larger digital systems. Now looking at the RS flip-flop on the left side, we notice something very different. It does not use a clock signal at all. It is asynchronous, which means it responds immediately to changes in its inputs. S and R. For example, at T2, S is 1 and R is 0, so the flip-flop sets the output Q to 1 without waiting for any clock. At T2, S becomes 0 and R becomes 1, which causes the output Q to reset instantly. This immediacy can be both an advantage and a disadvantage. While it responds faster, it also means the current circuit is more sensitive and can be affected by glitches or noise. So to summarize, the JK flip-flop is slower to react because it's clock controlled, but it is much more stable and ideal for synchronized systems like counters and registers. The RS flip-flop, being asynchronous, is quicker but can be unreliable in complex systems if not used carefully. RS flip-flops are simple and fast for certain tasks but limited by the embedded state. JK flip-flops, thanks to their toggle function, are great for building binary counters and more complex sequential circuits. Applications of RS flip-flop. RS flip-flop are data storage device used to store binary information. It is used mainly in the devices that requires binary information. It is used in asynchronous counters, shift registers, state machines, debouncing circuit, address decoding, clock synchronization. Applications of JK flip-flop. JK flip-flops are mainly used in counters, registers, frequency dividers, memory elements, finite state machines, FSMS, data synchronization. To summarize, RS flip-flops are easier to understand but not always reliable due to their undefined state. JK flip-flops solve this and are foundational in many digital systems, but both are essential in sequential circuit design. Thank you for your kind attention. Feel free to ask any questions about the working or application of RS and JK flip-flops.